Out on the Wyoming plains, long after the last highway lights have disappeared, the railroad is still awake. At first, there is nothing to see, just two steel rails running into black country, a signal glowing in the distance, and the wind moving low over the sagebrush. Then the sound arrives before the train does, not the sharp bark of a steam locomotive, not the steady thump of an ordinary diesel. This is a continuous mechanical howl, like an aircraft engine has been dropped onto the tracks. Just listen to the kind of sound people remembered. Then the headlight breaks over the grade. Coming out of the darkness is a Union Pacific gas turbine-electric locomotive, a three-part machine nearly 180 feet long. Up front is the cab unit, behind it a turbine unit packed around a jet-age power plant. Behind that, a fuel tender feeding it thick, cheap bunker fuel by the thousands of gallons. This was the big blow, built by General Electric to drag enormous freight trains toward the mountains with power few locomotives had ever matched. So if it was that strong, that advanced, and that unforgettable, why did it disappear? By the late 1940s, American railroading was caught between two eras. Steam locomotives still had the muscle, but they were expensive, dirty, and labor-intensive. Diesels were cleaner and easier to maintain, but the early road units did not yet have the sheer single locomotive power that the biggest steam engines could deliver. Union Pacific felt that problem harder than almost anyone. Its main line connected Council Bluffs, Iowa, with Ogden, Utah, and that route was not a gentle prairie railroad for very long. Westbound freight had to climb across Nebraska, Wyoming, and Utah through long stretches of grade where tonnage, wind, altitude, and distance punished underpowered trains. For decades, Union Pacific had answered that problem with giant steam. The railroad owned Challengers and Big Boys because it needed locomotives that could move enormous freight trains over the Wasatch and Wyoming grades without stopping every few miles for help. Those machines were built for brute force, and on the right assignment, they were exactly what the railroad needed. But steam came with a hidden bill. It needed water, coal, or oil, roundhouses, ash pits, boiler work, and large crews of skilled labour just to keep moving. A steam locomotive could be powerful, but it was also a rolling maintenance project. Diesel-electric power promised a different future. Electric traction motors gave smooth pulling force at low speed, and the engines could run longer between servicing. The catch was horsepower. A typical diesel road unit of the period could not simply replace a big boy by itself. So railroads solved the problem by coupling diesel units together. 2, 3, 4, sometimes more locomotives would be connected in a consist, all controlled from one cab. That worked, but it turned the heaviest trains into long strings of machinery before the first freight car even appeared. Union Pacific wanted something more elegant and more extreme. A locomotive with the operating advantages of diesel-electric transmission, but with steam-era levels of power concentrated into one commanding machine. That search for modern brute force opened the door for General Electric, and for a very different kind of engine. General Electric's answer was not to build a better diesel engine, it was to remove the diesel engine entirely and put a gas turbine inside a locomotive. The idea sounds strange until the pieces are separated. A gas turbine begins by pulling in air and squeezing it through a compressor. Fuel is then sprayed into that compressed air and burned. The result is a stream of extremely hot, expanding gas, and that gas rushes through turbine blades, spinning a shaft at very high speed. Just listen to the kind of machine General Electric wanted to bring to the railroad. But here is the important part. The locomotive was not being pushed down the track like a jet aircraft. There was no blast of exhaust acting as the main force moving the train. The turbine was there to turn machinery inside the locomotive. In General Electric's design, the turbine shaft drove a generator and later an alternator which produced electricity. That electricity flowed to traction motors mounted near the axles. Those traction motors turned the wheels just as they did on a diesel-electric locomotive. So mechanically, the concept was less alien than it first appears. Union Pacific crews were not being asked to operate a rocket on rails. They were being offered a familiar electric drive locomotive with a radically different prime mover. The diesel engine in a diesel-electric is basically an onboard power plant. It burns fuel, turns a generator, and sends electricity to the traction motors. General Electric's proposal kept that same basic chain, but swapped in a turbine that was compact for its output and capable of producing huge horsepower from a single unit. That made the idea bold but logical. Aircraft and industrial turbines had already shown that tremendous power could come from relatively small machinery. Railroads needed power, and Union Pacific needed it in enormous quantities on long western grades. The question was whether a turbine built for steady high-speed rotation could survive the dirty stop-and-start, fuel-hungry world of freight railroading. General Electric and Union Pacific were willing to find out, and the first experiments would turn this theory into one of the loudest locomotives ever to touch steel rail. The attraction was simple. A turbine could make an enormous amount of power without the bulk of a huge piston engine. A conventional diesel engine had crankshafts, connecting rods, pistons, valves, and thousands of repeated impacts happening every minute. It was strong, proven machinery, but it was heavy machinery. A gas turbine produced power through continuous rotation. Air flowed in, fuel burned, blades spun, and the output shaft kept turning at high speed. That gave the turbine a remarkable power-to-weight ratio. For a railroad trying to move heavy tonnage across long distances, that mattered. More horsepower from a smaller prime mover meant a locomotive could concentrate more of its weight and space on generators, electrical gear, fuel, and traction equipment instead of carrying an enormous engine block. The turbine also looked mechanically elegant. It did not have dozens of pistons slamming up and down inside cylinders. Its major rotating assemblies were comparatively few, and in theory that meant less pounding, less vibration, and smoother high-power operation. For a railroad that wanted to keep freight moving across the West, a machine happiest at steady, continuous output sounded almost purpose-built. But the same trait that made the turbine so appealing also hid its biggest flaw. Gas turbines are at their best when they are working hard. At idle, low speed or partial load, they keep moving large volumes of air and burning fuel without producing much useful work. A diesel could throttle down and become relatively economical. A turbine, by comparison, could be brutally wasteful when it was not being pushed. That was not a small problem for railroads. Freight locomotives do not spend every second climbing a grade at full power. They wait in yards, slow for signals, drift down grade, and sit while crews and dispatchers sort out the railroad around them. Union Pacific's apparent answer was fuel. If the turbine was going to be thirsty, then it needed to drink something cheap, not premium diesel fuel, but low-cost heavy fuel oil, the kind of refinery byproduct that railroads could buy for far less. On paper, that changed the equation. If the engine consumed more fuel, but the fuel cost much less, the economics might still work. The fuel Union Pacific had in mind was not ordinary diesel. It was heavy residual fuel oil, often described as NOM5 heavy fuel or bunker B, and it sat near the bottom of the refinery barrel. After lighter products like gasoline, kerosene, and diesel were drawn off, this darker, heavier material remained as a low-value byproduct. That low value was the attraction. Railroads bought fuel in enormous quantities, and even a small difference in price could reshape the cost of moving freight. If a turbine burned more gallons than a diesel, but those gallons were dramatically cheaper, the turbine's appetite could be turned from a fatal weakness into an acceptable trade. The catch was that this fuel did not behave like diesel fuel. When cold, it was thick, sticky, and nearly molasses-like. It did not flow easily through pipes, pumps, strainers, and injectors. Before it could be moved and burned properly, it had to be heated to roughly 200 degrees Fahrenheit, thin enough to pump and atomize inside the combustion system. That meant the locomotive was not just carrying fuel, it was carrying a fuel handling system. Tanks, lines, and equipment had to keep the oil warm enough to use. If the fuel cooled too much, the system could become sluggish or blocked. The cheap fuel came with plumbing, heat, maintenance, and operating discipline attached to every gallon. Union Pacific accepted that complexity because its operating profile seemed to fit the machine. These locomotives were not meant for light switching or stop-and-go branch line work. They were aimed at long, heavy freight runs across open territory where the turbine could stay under sustained load for hours. In that setting, the fuel burned steadily, the power stayed high, and the economics looked strongest. On paper, it was a clever match, a hungry engine paired with a bargain fuel on assignments where both could perform at their best. The turbine got the hard work it needed, and the railroad got horsepower that might cost less to use than it looked. But the entire bargain rested on two assumptions. The fuel had to remain cheap, and the railroad had to keep it manageable in daily service. If either side of that equation changed, the big blow would stop looking like a breakthrough and start looking like a very expensive gamble. Union Pacific did not jump into turbine power on faith. Before the railroad ordered a fleet, General Electric built an experimental machine to prove the basic idea in real railroad service. It was simply numbered 50, and in 1949 it went west to run on Union Pacific rails. Number 50 was not yet the famous production big blow, but it carried the essential concept: a gas turbine driving electric traction motors built for sustained high horsepower rather than low-speed switching. General Electric had already worked with turbine technology outside the railroad world, and the company believed the same kind of prime mover could be adapted to heavy freight. The test was a serious trial, not a staged demonstration for photographs. Union Pacific put the locomotive into the kind of work that mattered: long hauls, heavy trains, and wide open territory where a turbine could stay at high output. Engineers watched fuel use, reliability, maintenance demands, and how the machine behaved compared with the best diesel-electric power of the day. What they saw was enough to keep the project alive. The turbine could pull hard for long periods, and that was exactly the job Union Pacific wanted it to do. It was loud, unusual, and mechanically different from anything else on the roster, but it was not treated as a curiosity. It was treated as a possible answer to a real operating problem. The timing also mattered. By the early 1950s, freight tonnage was growing, train weights were climbing, and railroads wanted more power without endlessly adding more diesel units to every consist. A single turbine electric locomotive promised a large block of horsepower in one package, with the potential to burn fuel that cost far less than diesel. So Union Pacific moved from testing to procurement. In 1952, the railroad ordered 10 production gas turbine locomotives rated at 4,500 horsepower. After that first order, it committed to 15 more. That was not the behavior of a railroad buying a gimmick. That was a railroad spending serious money because the evidence from number 50 suggested the gamble could pay. The experiment had done its job. It turned the turbine from an engineering proposal into a locomotive program, and it gave Union Pacific the confidence to build a fleet around one of the boldest power ideas in American railroading. The turbine program did not stop with the early production fleet. General Electric and Union Pacific kept pushing the idea until it reached its final and most extreme form. 30 turbine sets rated at 8,500 horsepower each. These were delivered between 1958 and 1961, and they were numbered 1 through 30. On paper, that rating was enormous. In railroad terms, it meant Union Pacific could put a block of power on the front of a freight train that few machines in the world could match. The design was not a single locomotive in the ordinary sense. Each set was built as a three-part system: an A unit, a B unit, and a fuel tender. The A unit carried the cab and diesel equipment used for starting, hostling, and low-power movement. The B unit held the gas turbine and the main electrical generating machinery. Behind them came the tender, loaded with the heavy fuel oil that made the whole concept economically attractive. Put together, the consist looked less like one locomotive and more like a small power plant on rails. It had the length, the mass, and the operating presence to match its horsepower rating. Union Pacific itself described these machines as among the largest and most powerful locomotives of their era, and that was not promotional exaggeration. In the late 1950s, 8,500 horsepower in one locomotive set was a staggering figure. This was the version that became most strongly tied to the nickname Big Blow. The name came from the turbine's tremendous exhaust and the way the machine announced itself under load. It was not just loud in the usual locomotive sense, it had a hard, continuous turbine roar that carried across yards, canyons, and open desert. For Union Pacific, the 8,500 horsepower turbines were the peak of a decade-long experiment. The railroad had started with a test machine, moved into production power, and ended with a fleet of giant three-section locomotives built for the biggest freight assignments in the West. Inside the big blow, the A unit was the part that looked most familiar to a diesel locomotive crew. It had the cab, the engineer's controls, brake equipment, and the auxiliary machinery needed to make the whole set usable in normal railroad service. This was where the crew actually ran the locomotive, even though the biggest source of power sat behind them. The A unit also carried a diesel engine, but its job was not to provide the headline horsepower. It was there for starting, moving around terminals, and handling low-speed work when lighting off the turbine would have been wasteful. In a yard, the crew could use diesel power to reposition the set without bringing the gas turbine into full operation. That mattered because turbines were at their best when they could run hard for long periods, not when they were idling and creeping through switches. Behind the A unit was the B unit, and this was the heart of the machine. It carried the gas turbine itself, along with the main generator that turned turbine power into electricity for the traction motors. The turbine did not drive the wheels through a mechanical transmission. It spun generating equipment, and that electrical output fed the motors on the locomotive trucks. That arrangement made the big blow a locomotive in form, but a power station in function. Air entered the turbine, fuel was burned at high temperature, and the resulting energy spun the machinery that produced thousands of horsepower worth of electrical power. The system was built around sustained output, the kind needed for long freight trains climbing grades across Union Pacific territory. Then came the tender, which was not an accessory in the casual sense. It was a necessary part of the locomotive set. Union Pacific used converted tenders to carry heavy fuel oil in enormous quantities, measured in tens of thousands of gallons. The fuel had to be heated so it would flow properly because the attraction of the turbine program was that this thick, low-cost fuel could be burned in huge volumes. That tender gave the big blow the range to work long distances without stopping constantly for fuel. It also completed the logic of the design. The A unit handled control and low power movement, the B unit produced the main force. The tender supplied the fuel needed to keep the turbine fed. Seen this way, the big blow was not just a big locomotive with an unusual engine. It was a three-part industrial system built to turn cheap heavy fuel into continuous horsepower, hour after hour, across some of the hardest freight routes in the American West. The big blow made the most sense on the kind of railroad that Union Pacific had in abundance. Long, open main lines where a locomotive could settle into heavy work and stay there. Across Nebraska, Wyoming and Utah, the railroad had miles of territory where trains were not constantly stopping, switching, or crawling through dense urban trackage. Freight could move over long distances with the throttle open, and that was exactly where a gas turbine began to justify itself. The machine did not want short bursts of power, it wanted a sustained assignment, a heavy train, and enough room to run. On those routes, Union Pacific could use the turbines on freight that demanded enormous horsepower for hour after hour. Coal, merchandise, and other heavy consists could be handled with fewer separate locomotive units than a comparable diesel lash-up of the same era. Instead of assembling a long string of smaller locomotives, the railroad could put one turbine set on the point and get a huge block of power from a single purpose-built machine. That mattered operationally. Fewer units meant fewer engines to coordinate, fewer individual prime movers to maintain on that train, and a simpler way to put very high horsepower into service on the right assignment. The turbine was not delicate in the sense of being weak. When it was fed properly and kept in its intended environment, it could do exactly what Union Pacific bought it to do: pull hard, keep pulling, and make use of cheap, heavy fuel. This is the part that often gets lost when the big blow is treated only as a failed experiment. It was not built for every railroad, every route, or every kind of service. It was built around a very specific operating theory, that on broad western main lines, with long grades and heavy freight, sustained turbine power could pay its way. That theory had real limits, but it was not fantasy. In the right territory, the Big Blow was useful enough to remain part of Union Pacific service for years. Its problem was not that it could not work, its problem was that it needed a narrow world to work well, and railroad economics were about to make that world much harder to find. What gave the Big Blow its nickname was not just volume, it was the kind of sound people associated with airports, not freight yards. When the turbine was working, its exhaust did not come in the familiar pulses and growls of a diesel locomotive. It was continuous, harsh and high-powered, a mechanical roar that could ride over the rest of the train. For a few seconds, the best narration is almost none at all. Just the image of a Union Pacific turbine leaning into a heavy freight, with that jet-like blast filling the scene. That sound made the locomotive unforgettable. Crews, rail fans and people living near the line could identify it before they ever saw it. The name Big Blow was not a marketing phrase. It came from the way the machine announced itself across the landscape. But the same feature that made it legendary also made it hard to live with. On open western routes, the noise could scatter into empty space. In more populated territory, it became a complaint waiting to happen. Union Pacific tested the turbines beyond their best-known territory, including routes such as Salt Lake City to Los Angeles. Those trials did not last, partly because the noise was unpopular in more crowded areas along the line. A locomotive that sounded spectacular in the desert could become a public nuisance near towns, terminals and commuter corridors. So the Big Blow carried its own boundary with it. The roar proved how powerful it was, but it also helped decide where that power could be used. The fuel that made the turbine economical was also what made it troublesome. Union Pacific did not want to burn premium diesel in a giant gas turbine. The attraction was residual fuel, the heavy leftover oil from the refining process. It was cheap, thick, and available in huge quantities. On paper, that made perfect sense for a railroad trying to move enormous freight trains across long distances. But residual fuel was not clean fuel. It could carry ash, trace metals, sulfur compounds, sand-like grit, and other contaminants that a normal fuel system would rather never see. Before it could even be used, it often had to be heated so it would flow properly. Then it had to be filtered, pumped, and delivered in a way that a precision turbine could tolerate. That was the hard part. A gas turbine is not a furnace with wheels. Inside it are compressor and turbine blades spinning at extreme speed, with tight clearances and hot gas rushing through carefully shaped passages. When dirty fuel burned, some of its unwanted material did not simply vanish out the exhaust. It could leave deposits on blades, nozzles, and internal surfaces. Those deposits changed the machine. A thin build-up could disturb airflow and reduce efficiency. An uneven build-up could create imbalance. In a rotating assembly moving at thousands of revolutions per minute, imbalance was not a small annoyance. It meant vibration, stress, and the possibility of damaged parts deep inside an expensive engine. Maintenance crews had to fight the fuel as much as they serviced the locomotive. Filters needed attention. Heating equipment had to work. Fuel handling became its own job. The turbine itself demanded specialized inspection and cleaning because deposits in the wrong place could turn cheap operation into a costly shop visit. Union Pacific and General Electric tried to manage the problem. Different fuels were tested. Some turbines were modified to burn cleaner fuels during startup or at lower loads. Propane firing was explored as a way to avoid some of the worst residue problems. These ideas helped in certain situations, but they did not erase the basic conflict. The Big Blow was built around a bargain. Use low-cost fuel to produce massive horsepower. The catch was that the low-cost fuel brought its own bill. It moved the expense away from the fuel invoice and into heaters, filters, inspections, cleaning, downtime, and turbine parts. Cheap fuel was never simple fuel. In the Big Blow, it was a maintenance problem disguised as an operating advantage. While Union Pacific was fighting the turbine's fuel problem, the ordinary diesel-electric locomotive was getting better at almost everything that mattered. In the 1950s and 1960s, diesel builders kept raising horsepower, improving electrical gear, and making engines more dependable. A road locomotive no longer had to be a modest replacement for steam. It could be a high-mileage freight machine with standardized parts, trained mechanics, and a growing record of predictable service. The most important advantage was not just inside one locomotive, it was in the way several locomotives could work together. With multiple unit control, one crew in the lead cab could operate 2, 3, 4 or more diesel units as if they were one machine. The throttle, brakes and traction controls could be commanded from the front, while every unit behind added its own power to the train. That changed the horsepower problem. A railroad did not need one enormous prime mover to pull a heavy freight across the West. It could assemble a set of conventional diesels, match the power to the tonnage, and break the set apart when traffic patterns changed. A locomotive that hauled coal one week could be reassigned to intermodal, grain or general freight the next. It also changed the risk. If one diesel in a multiple unit consist failed, crews could cut it out, send it to the shop and keep using the remaining units. A turbine failure was different. When the giant engine at the heart of the big blow was out of service, a massive block of horsepower disappeared with it. For maintenance departments, modular power was easier to live with. Diesel shops already handled pistons, injectors, traction motors, generators and electrical cabinets. Parts could be stocked across a fleet. Mechanics could move from one unit to another without treating each locomotive like a rare machine with its own special rules. The turbine still had brute force. At full song, it could deliver a level of power that made diesel sets look ordinary. But railroading is not a contest of peak output alone. It is a business of availability, repair time, fuel cost, routing flexibility, and how many tons actually move over the road every day. By the time the diesel-electric matured, the big blow's original argument had weakened. Its size was no longer the only practical path to huge horsepower. The diesel fleet could build that horsepower one unit at a time and fix it the same way. The big blow did not vanish because it suddenly became useless. It vanished because the business case that once made it logical slowly fell apart. Union Pacific had accepted the turbine's appetite because it burned a fuel that was cheap enough to make the trade worthwhile. The locomotive used heavy residual fuel, the thick leftover product from petroleum refining. In the right market, that was a bargain compared with the higher grade fuel used by diesel locomotives. But refining did not stand still. As oil companies found more profitable ways to process crude, the leftovers became less of a waste product and more of a usable feedstock. Residual fuel was still available, but it was no longer the unbeatable discount that helped justify a machine with such extreme consumption. That mattered because the gas turbine was thirsty by design. In broad terms, a big blow could consume roughly around twice as much fuel as comparable diesel-electric power doing similar work. When the fuel was cheap, that penalty could be defended. When the price gap narrowed, the turbine's greatest operating weakness moved directly onto the balance sheet. Fuel was only one part of the bill. The turbines ran hot, handled dirty fuel, and lived hard lives in mountain freight service. Filters, fuel systems, turbine parts, electrical equipment, and support machinery all demanded attention. As the fleet aged, the cost of keeping these specialized locomotives available grew harder to absorb. A conventional diesel fleet did not need to beat the turbine in a one-on-one contest to win the argument. 3 or 4 ordinary units could provide the needed horsepower, fit into existing shops, share parts with the rest of the roster, and be reassigned as traffic changed. If the railroad needed less power, one unit could be removed. If it needed more, another could be added. The turbine was extraordinary, but it was not flexible. It made the most sense on long, heavy, high-priority runs where its full output could be used often enough to justify its cost. As railroad operations changed, that narrow sweet spot became harder to protect. By the late 1960s, Union Pacific was no longer choosing between power and weakness. It was choosing between one spectacular machine with expensive habits and a growing diesel system that was easier to fuel, repair, schedule, and replace. The big blow still had strength, but the railroad no longer needed strength at that price. The end came quickly for the biggest turbines Union Pacific ever owned. The 8,500 horsepower fleet was retired mainly in 1968 and 1969, as the railroad moved decisively toward conventional diesel-electric power. By 1970, Union Pacific's turbine program itself was over. Withdrawal did not lead to a quiet second career. These locomotives had been built for a very specific job, with unusual fuel systems, turbine equipment, and support needs. Once they no longer fit Union Pacific's operating plan, there was little practical market for them elsewhere. Most units were dismantled after retirement, their massive bodies reduced to parts and scrap. That makes the survivors especially important. One of the best known examples is number 18, preserved at the Illinois Railway Museum. It stands as a rare public example of the big blow era, a machine built at a scale that still looks extreme even decades later. Another major survivor is number 26 and 26B, displayed with its tender at Ogden, Utah. That set is especially powerful because it shows the locomotive as a system, not just a cab unit. The tender was part of the answer to the turbine's appetite, carrying the fuel that allowed these machines to work the long western grades they were designed for. These remains do not represent a failed curiosity. They represent a serious attempt to solve a real railroad problem with the tools and assumptions of its time. Union Pacific needed enormous horsepower for heavy freight across demanding territory, and GE offered a machine that could deliver it in a way no ordinary diesel unit could match alone. For a brief period, the answer looked like a turbine. Then fuel economics, maintenance demands, and operating flexibility moved the future in another direction. The preserved big blows are physical reminders of that moment when one railroad tried to meet tomorrow's traffic with a locomotive that sounded, looked, and performed like nothing else on the rails. The big blow was never just a monster built for spectacle. It was a calculated answer to cheap, heavy fuel, long western grades, and freight trains that demanded more power than ordinary diesel sets could easily provide. Its strength was real, so were its limits. The turbines delivered astonishing horsepower, but they brought extreme noise, heavy fuel consumption, and maintenance needs that only made sense inside Union Pacific's specific operating world. When that world changed, the equation changed with it. Better diesel electrics, rising fuel concerns, and the value of flexibility made several ordinary locomotives more practical than one extraordinary machine. If you want more stories about machines that were brilliant in one narrow moment, subscribe to the channel. Thanks for watching, and tell me in the comments which strange railroad experiment you think deserves a full episode next.